We're in the chapter 4. Just like other chapters, so some sections I emphasize and some sections I just skim, and you can skip completely. So here in chapter 4, I'm going to talk about the conduction shape factor. It will solve a problem with it. And then I'm going to talk about an energy balance to solve for two-dimensional steady state temperature field. It's a conduction in a two-dimensional domain. It's really a finite difference technique that we're going to employ. And what we get, one differential equation valid throughout the whole domain is replaced by a bunch of algebraic equations to expressed as energy conservation at unique locations in the domain. So let's go ahead and jump into it. Conduction shape factor. This is equation for Q is equal to K, A over L, T1 minus T2, or some delta T. We tried to read into this equation. Here's a flow of heat. This is a temperature difference. So I may have a slab, and everywhere along this edge of the slab is T1, and everywhere along this edge of the slab is T2. So T1, a lot of times we think about it as a point, the temperature at a point, but it could be the temperature at a face, or the temperature along an edge, or temperature over a surface. And then T2 is a temperature that's uniform over another point, or line, or edge, or surface. But I know that the wall we approximate down to a point. We say, oh, that's T1 at that point and T2 at that point, but it's really a face. It represents uniform temperature over a face. That's what drives the flow. What is K? Well, that's a property of the material, thermal conductivity. I could put different material in here and I'd get greater heat flow or less heat flow. I could have a high conductivity material like a metal, or a low conductivity insulation materials. But this, we haven't emphasized that. What is area? Area. What's length? Length. Think about the units, SI units, meters squared per meter. What is the unit for A over L? It's meters, right? That's a bad looking squared, sorry about that. Meter squared divided by meters is meter, unit. And so what does it represent? It doesn't represent what drives the flow, or what resists the flow coming inherently from the material. It represents the shape. And so they give it a name. They're going to say Q is equal to K, S, the symbol S, shape S, times delta T. And so what they found was we can talk about a bunch of different heat transfer problems, and if I could get the shape factor for that geometry, then it's pretty easy. So think about this heat transfer problem. I have a box and a pipe in the box. So think about it going way back in 3D, right? And so that pipe is going way back. And everywhere on the outside surface of the box is a temperature T1, and everywhere on the inside pipe it's temperature T2. And you know what? The rate of heat transfer via conduction from the inner uniform temperature cylinder to the outer box could be expressed as Ks delta T. I just need to get that shape factor for the geometry. That's what I need to do. Well, they have a table of a lot of shape factors. A lot of textbooks will have it. So here is different cases. This is a horizontal isothermal cylinder of length L. You have to look at the illustration, get all the characteristics of diameter and depth, burial depth. It's buried in a semi-infinite medium, and so the top surface is at T2. The bottom pipe, the isothermal cylinder, is all at T1, and they want to say, what is the heat transfer that's going to go from that buried cylinder up to the surface? So the flow of heat will be like this, going that way, and coming off of the cylinder. How come there's nothing down here? Well, they don't have T3. They don't have 3 temperatures. It's like this is semi-infinite, and it just goes on forever and ever and ever. And if the heat's going to come off of this temperature, think of the T1 being high and T2 being low, it's eventually all going to go to T2. Okay. if that's true, you can get a shape factor. Here's two equations for the shape factor depending on how L and Z depend. So if L is much, much greater than D, then use this one. L much, much greater than D plus Z greater than 3D over 2, then use this even simpler equation, but otherwise use this one. Somebody did a lot of work, didn't they, to get the shape factor? And it's all geometrical information. You have to have in there where T1 and T2 are. They're the constant temperatures. Let's solve a problem. So we have an electronic device in the form of a disk that's 20 millimeters in diameter. It dissipates 100 watts when mounted flush on a large aluminum alloy block. So this aluminum is large. We look up the thermal conductivity of the aluminum, 177 watts per meter degree C. This block is large. What's the key word there? Large aluminum block. It's semi-infinite. It's a semi-infinite. From the perspective of that little electronic device, it's sitting on a huge. The block maintained a temperature 27. What do they mean by this TB equal to 27 degrees C? Does that mean the temperature immediately right below that hot heat dissipating electronic device is 27, or the temperature some far away? It's far away. It's far away in that quote-unquote semi-infinite material, that aluminum block. Now, the mounting arrangement is such that there's a contact resistance, R double prime TC. I shared with you that notation always gives me fits. I've got to go slow right here because I often make an error with this. And it's 5 times 10 to the minus 5 meters squared, funny units, K per watt. And that's between the device and the block. Only part A do we want to talk about. Part B is if you put on a finned heat sink on the top of it. Oh, it's worthwhile investigating, but we don't have time. Okay? So put a finned heat sink on it and then analyze it again. Well, let's just look at part A. So part A says calculate the temperature the device will reach, assuming that all the power generated in the device must be transferred by conduction to the aluminum block. So there's no convection taking away some of that 100 watts. All the 100 watts goes into the block. So how do we solve this problem? Use a thermal network to help organize your work. And so you introduce temperatures at specific nodes, and they have meaning for where you have a temperature measurement. One of the nodes will be the temperature of the device that we're interested in solving for, true? The electronic device temperature. Then, that's this temperature right there. Then another one will be the temperature of the block far away. But what offers resistance to heat transfer? There's two things that offer resistance to heat transfer. One is getting it through that epoxy. True? Isn't it getting it through the epoxy? So that resistance is equal to, it's R double prime TC divided by area. And if I do it right and I look at the units, won't this give me how many degrees C temperature drop will be there across that resistor per watt of flow? Okay, and then this one, what is that resistance? Well, it's L over Ka, but we just called A over L to be S, shape factor. So S is A over L, it's our shape factor, true? So this really helps us. What is this temperature here? It has some meaning. It's the temperature of the aluminum immediately below the device. It's not the device temperature, it's the aluminum right below it. Okay. How about once we have this organized, we know that we have 100 watts coming in. What we do is we say, go ahead and calculate the area and then calculate this resistance right here, this R. This resistance for the first one is 0.1412 degrees C per watt. The resistance for the shape, but I need to get that conduction shape factor. Go to the table, look for the case that applies, if there is one, They have a disk of diameter d and temperature T1, so this is all the same temperature right here. And it's a semi-infinite material temperature and conductivity, so this temperature far away is T2. It looks like it works, so our conduction shape factor is 2d, to the diameter. So I can jump back and I say, oh, I know what S is. That's 2d from their table. And so that resistance comes in at 0.1592 degrees C per watt. I sum them up. I get the total resistance of two resistors in series, 0.3004 degrees C per watt. Maybe I go back and I say, what was the percent contribution due to the epoxy? Almost half. And then the resistance due to the aluminum block is almost half. So we find that we now can compute the temperature of the device, knowing that this temperature of the block far away is 27 degrees C, is equal to the temperature of the block far away plus how much heat is being dissipated times the resistance total, and it comes in at 57 degrees C. We're building on some of the concepts that we've already constructed in this class. So it look reasonable? Make sense? All right, let me press forward. Okay, I'd like to ask a clicker question, and it's the same problem that we just discussed. And the clicker question reads, if the heat transfer rate is increased above 100 watts, now you're not just putting in 100 watts, think about putting in 150 watts or 200 watts, right? It goes up higher than 100 watts. How will the device temperature change? Will it increase? Will it remain the same, not change? Or will it go down? What will the device temperature do? Is everybody in? Sure. All right, let's go ahead and stop it then. Let's stop and let's go back and look. We developed this equation right here, right? So let me just rewrite it over here and say the device temperature is equal to the temperature of the aluminum block far away plus how much heat you're dumping through the block, the device that has to go out in the times the total resistance, thermal resistance, right? So if Q goes up, what does the temperature of the device do? It goes up. So, I'm not trying to be tricky, but now let's solve another problem. This problem right here. Okay, this one's a little more challenging. If the block material is changed from aluminum to copper, how will the device temperature change? So leave Q alone, the same 100 watts. If I just say, no, don't use aluminum, use copper, how will TD change? Did I give you enough time, everybody in? All right, we'll go ahead and stop it then. Before I grade that one, let me do this. Let me ask a quick clicker question. I want to compare the thermal conductivity of copper with the thermal conductivity of aluminum. Somebody says, I think the thermal conductivity of copper is greater than aluminum. No, somebody says it's equal to. Somebody says, no, it's less. So answer A, B, or C. How does the thermal conductivity of copper compare to aluminum? Is everybody in? So let's go ahead and stop. So isn't copper a higher conductivity? It is. So unfortunately, 4 of you, even if you thought the right way, you had it backwards on K, and so you're going to mess up on the next question. Let's go back and grade the previous question. So if I switch to put a higher thermal conductivity into this block down here, it'll reduce the resistance to heat transfer through that block. Hence, the overall resistance to heat transfer will go down. The overall resistance to heat transfer will go down for the same Q. Hence, the device temperature will go down. So a lot of you were correct. All right, very good. Let's press forward. We want to talk about solving the heat diffusion equation, not analytically, but numerically. And we want to solve it for what we call two-dimensional steady-state conduction, because that's our domain. We're talking about two-dimensional steady-state conduction. So I'm interested in, if I have a domain like this, what I'll do is I'll discretize it, and I'll solve for the temperature at those points. Analytically, if I got an analytic expression, it would give me the temperature at any x or any y. But I'm interested in solving for it at basically what they call a grid. You may have seen this. Hopefully you've seen this, numerical methods. So we introduce a grid where we have the nodes are located every delta x spacing. And the nodes are located every delta y spacing. Now, for this introductory purposes, don't say, oh, delta x starts to get larger as I move further to the right, or smaller as you can do that. You could do it in the computer code. But for introductory purposes, keep the mesh spacing constant throughout. And often, the mesh spacing in the x is equal to the mesh spacing in the y, but it doesn't have to be. But for introductory purposes, it's easy if it's just a nice square grid. And what you're doing is you're looking to calculate the temperature at this location, this location, this location, at those particular nodes. You could number them. You could say, oh, this is the location 1, this is location 2, this is location 3, 4, 5. Or you could say, oh, we're going to talk about its location in the x. This will be the I minus 1, this will be the I plus 1 indice. And maybe this will be the j minus 1 and the j plus 1 indice. And then I would be talking about, oh, I need to calculate the temperature at this location, and I would refer to it as the temperature at location I for the x location, comma, j for the y location. Not too tricky. How about this one? What is that one using this subscript notation? What is it in the I? And what is it in the j? J minus 1. Let's go for this one right here. I plus 1, j plus 1. Right, you got it. Now, what we do is we have to define very clearly, for introductory purposes, what is the zone for each of those nodes. And you would just do it like this. Cut. Here's a boundary between edges. Here's a boundary between edges. Boundary between edges, boundary between those lines. And so guess what? That's the volume associated with the node Tij. What's the volume associated with the node, this node right here, which is Ti plus 1j? It would be like that, right? Not too tricky, but you have to be really clear about what is the volume associated with each node. Now I want to numerically solve for the temperature at those nodes. So what do? I write an energy balance for each node. The book describes both a mathematical approach as well as an energy balance approach. The mathematical approach says, well, what's my governing heat diffusion equation in this domain? It's steady state, two-dimensional. Isn't it something like the second derivative of temperature with respect to x squared? Put a partial derivative because it's not only a function of x, but it's a function also of y. True? Plus q dot divided by k equal to 0. You could have heat generation in that material, but otherwise it's just conduction. Did I leave anything out? It's steady state, no transient part, and it's only two-dimensional. Let's leave it in the rectangular system. What they do is they say, what we're going to do is introduce a grid, and then we're going to have this location. And what we'll do is approximate that x derivative, go back to numerical methods. Temperature minus 2 the temperature plus the temperature divided by delta x squared. Now it's just, okay, what syntax do we have for our locations? I used the I and J just a minute ago, right? The book is using the M's and the N's. Can you see that? M and N. So let's stay with the book. If I want to approximate the second derivative temperature with respect to x, it would be temperature Mn. Then it would be the temperature at M plus 1 comma N. And temperature at M minus 1 comma N, or you could switch these locations either way, but it's a plus and a minus. I'm done with that. All right. Do the same thing for the derivative here, and then get a bunch of algebraic equations, link them together. I don't prefer the mathematical approach. I prefer more intuitive energy balance. So here's the illustration, right? And so you say, here's the interior node. Its zone of or control volume associated with that node is shaded pink, and there's a red dashed line indicating the boundary, which there could be flow across it. And you say, well, I could have flow in from the, what do you want to call it? From the right. I could have flow in from the left, Q from the top, Q from the bottom. And now I just work out the algebra. And it is good to develop a simple, like everything goes into the node of interest that I'm trying to write an energy balance for. So don't try and be tricky and say, well, I think it's hot over here and cold over here, and so this arrow's coming in, but this arrow's going out. It's better just to say all in. Got it? All right. So for this one, let's do Q in from the left. You would say, I have some thermal conductivity, some area. The area is going to be delta y tall and delta z into the third dimension. Doesn't that give me an area? Divided by length. The length is the distance between the two nodes. Wouldn't that be this distance? Which is the same as delta x. Times the temperature at M minus 1 comma N minus the temperature at Mn. It's driving from way I wrote it, a higher temperature outside node to the lower temperature interior node for that control volume. You then put the same thing for this one coming down here. That would be K. What would be my area? Well, it would be delta X times delta Z divided by the length, delta Y, times the outside area, the temperature outside, M, N plus 1 minus the temperature Mn. And then I would add to it, let's go from this side in, it would be K, what's my area? Delta Y, delta Z divided by my length, the distance, delta X, times T at M plus 1 comma N minus T at M comma N. Notice that this is always a minus M comma M. Minus T at M comma minus, and the same thing for this next one. Let's put K for this one coming up. Delta X times delta Z divided by delta Y times T at M comma N minus 1 minus T at Mn. Now let's say there is some strength of heat source, Q dot. Well, I would have another in, and I'd have Q dot times delta X times delta Y times delta Z. And finally, all of those summed up have to equal 0. What comes in has to go out. I have an algebraic equation. It represents an energy balance for that node. Let's solve a problem. Consider the square channel shown in the sketch operating under steady state conditions. So everywhere on the interior, it's 600 Kelvin. Everywhere on the exterior, it's exposed to a convective fluid at T infinity of 300 Kelvin and a convection coefficient of 50 watts per meter squared Kelvin. True? See that? Okay. From a symmetrical element of the channel, a two-dimensional grid has been constructed and the nodes labeled. So it's like if I take, this is a symmetry line or section right here and there. That's kind of the smallest symmetry section I can get. And then if you just think about flipping over those symmetry, you can go and get back to, go from 1/8 to 1/4, from 1/4 to 1/2, and from 1/2 to 1/2. That's how you think about those symmetry lines. But here it is, the cutout and blown up a little bit. And they introduced some nodes at temperatures, and they numbered them 1 through 9. So the temperature at node 1 is here, node 2 is here, node 3, and we're interested in calculating the temperature at each of these 9 locations. Now, this is kind of interesting because you have this diagonal symmetry section, true? We're going to have to think about that a little bit. All right. Now, what do? They tell us the temperature at node 1, this is 430 Kelvin. The temperature at node 3, that's right here, 394 Kelvin. The temperature at node 8 and 9, that's 600 and 600 Kelvin. And the temperature at node 6, 492. They just tell you, okay, I know this one, know this one. It's a made-up problem. Okay, what temperatures do they not know the value at? They don't know it at 2. They don't know the temperature at 4. They don't know it at 7. And they do not know it at 5. So, part A, begin with properly defined control volume. Good idea. What is the zone responsible for each of these nodes? You know, and then I have a boundary between me and my neighbor. And across that boundary there can be flow and an energy balance. I need to calculate that flow. And then write the finite difference equation or the energy balance equation for those nodes, and then you can solve for the temperature. So I would do this. I would say I see a grid, and so go halfway between those two x locations, and halfway between those two x locations, and halfway between those x locations. And then I would go halfway between those y locations and halfway between those y locations. And you can see that the node 6 has a pretty large volume, doesn't it? Where is the corner of the element, the block for 6, that little control volume for node 6? Isn't it right down here and touches the symmetry line? It sure does. So that's what it looks like there. Let's look at 5. What does 5 look like? Looks like that. What has a small? Well, 1 has a pretty small. But what even has a smaller? 4. 4 has even a smaller little section. And then 9 has this section. It goes like this. Okay? Now, what we want to do is write an energy balance for node 1. Node 2. So here's node 2 right there. I have convection off of this side for node 2. And the delta x, delta y is 0.01 meter. Okay. So what I'll do is I'll say this. Maybe I'll blow it up. Here's node 2. I'm thinking like this. I have some flow in from convection. I have some inflow from node 1. I have some inflow from node 3, and I have some inflow from node 6. The in from 1 and the in from 3 and the in from 6 are all conduction, and the in from T infinity is convection. All right, so I don't have any heat source, so I don't have to find the volume to multiply by Q dot. But if I needed to, I'd have to get the volume and then multiply by Q dot. So let's go ahead and write it. So how much comes in from T infinity? Won't it be H times that area? Is the area delta X times delta Z? And then T infinity minus T2. Is that what's flowing in from the convection into the node 2? Yeah. And then we're going to have flowing from, maybe I should have left it over here, flowing in from 1. I would have something where T1 minus T2. Okay, but what is it? It's K times appropriate area. The area is delta Y over 2 times delta Z. And then I divide by the length delta x. All those terms make sense? What do you think a lot of students may miss out on? They would leave off that factor 1/2. Don't leave off the factor 1/2. Where'd that? It comes from y over 2. That's the area. All right. And then we come from 6, so T6 minus T2. And we're going to have K, and we're going to have the area, delta X, delta Z, divided by delta Y. And then coming in from node 3 into 2, K, delta Y over 2, delta Z divided by delta X times T3 minus T2. All of that summed up has to equal to 0. 4 terms summed up has to be equal to 0. Otherwise, there won't be steady state energy balance for that node. Now, at this point, for this problem, I look and I say, you know what? I can cancel some of these terms. I can get rid of the delta X, delta Y because they are the same numeric value. True? And I can pick delta Z to be unity. I can just think about I'm going to do everything per 1 meter length, depth. That's fine. Okay? So I can pick delta Z equal to 1 meter unit depth. So it's like, okay, check, 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 check. All right. They give me the H. They gave me the K. Did they give me the temperature at infinity, the fluid temperature? Yes. Did they give me temperature at 1? Yes. Temperature at 6? Yes. Temperature at 3? Yes. And they gave me delta X is equal to delta Y 0.01. All these terms are given. There's only one unknown in this equation. It doesn't normally work out this way. Usually you have multiple unknowns with one equation, but for this problem, the energy balance for node 2 gives you one unknown with one equation. You can solve for T2. You can solve for T2. Let's do this. Get the energy balance for node 4. So this was for node 2. This is for node 4. Where is node 4? Right there. All right, clean it up just a little bit. There's the little element for node 4. How could you have heat transfer? Well, we're going to have it from the convective fluid, from 3. Do you have any other conduction from node 5, 6, 8, 9, 7? No. That's it. It's so node 4 balance just writes it like this. You've got to get your areas right. H times delta X divided by 2 times T infinity minus T4. Isn't that what's convected in? Okay. Plus K delta Y over 2 delta Z divided by delta X times T3 minus T4. Those equal to 0. Did that work? In the interest of time, I hate to do this, but I'm going to show you Excel, and I was going to develop this. What you can do is you can set up a whole matrix problem. You can implement this in matrices, right? Because you'll have like not one equation, one unknown. You'll have 10 equations with 10 unknowns. How do I solve that, Professor? Set it up, linear algebra. And so make a nice matrix. Put in your coefficients. This is the matrix A. AX equal B. Get your right-hand side, everything that doesn't multiply one of the unknowns. And a way you can write it that way. Set up a matrix AX equal B and then solve for it. Okay? For this problem, this is the solution. Why did I color code the blue? What is special about the A matrix along that blue line? What's that called? That's the diagonal. And notice I treated 1 through 9 as kind of variables, like temperature at 9 and temperature at 8 and temperature 7. They're all unknown. But when I looked at it, I said, put a 1 on the diagonal and 0 everywhere else in that matrix A. And then on the right-hand side, put the specified temperature, 430, And when I numerically solve this matrix problem, the only solution is the unknown x at T1. It will be 430. It's like I force that temperature to go to 430. Do you see that? Can you see I also did it for node at temperature 3? I forced it to go to 394. Guess what the solution is? 394. So all of the specified nodes, I put them in that way. And then this is an energy balance for the second node. Whoops. Right there. And notice that the second node plays with 1, 3, 6. But also way over here on the right-hand side, that's where T infinity comes in. Can you see that? T infinity comes in right there. So I wanted to go further than I did. Sorry about that. But I encourage you to set it up as a matrix problem and solve the homework problems that way that are challenging due next time. Okay? Thank you very much.